Here's Titan. Nerd, I know. So no, honestly, guys, I want you to talk. Don't worry about being quiet. If you're listening and you're quiet because you're listening, that's different. But again, this guy is an amazing guy. I'm looking at all of his publications. I actually went to Google Scholar and looked at a bunch of them. So again, his focus is exoplanets, extrasolar planets. Fancier term, same thing, synonymous. I haven't owned a TV in 10 years. By the way, if you don't see me on my screen, I'm still reading chat, and I'll say hi to you. If that won't even matter to you guys. You guys are already here. Why is it blue? So methane's a hell of a thing. I'm sure there's some nitrogen, maybe some CO2, some oxygen. Those rocks, if I'm correct, and we can ask him, but it's like frozen water. Again, we like liquid, guys. Liquid. We like liquid. Should have taken a selfie. Zeppy, I would have. Fuck. So here is some things we're going to discuss with him. Hey, Broton. Hi, you. I've been missing you. Haven't seen you in here. I've seen you other places. Love beer. And here's the surface. He knows a lot about the surface. Guys, if you have questions about this topography, it looks like this guy is obviously geologically active. So is Pluto. Hey, I don't want any ideas about that, though. You hear me right now? Don't want any ideas about that. I don't know if Dr. Stefan's in here. Dr. Stefan, if you are, have him turn on so he can actually see the chat. I would love him to see the chat. That was really cool that Emily Levesque. I can't botch this guy's name. Jason Barnes, I can't. But it is nice for them to see the chat. I know he has to mute me, but it is nice if he can see the chat. How you doing, Broton? So yeah, the topography is very interesting. Probably carved a little bit out of these methane lakes. We'll see. Guys, I really don't know a lot about Titan other than that it's pretty cool. It's pretty sweet. It's got this pretty thick atmosphere. Yeah. These are actual images. And again, anything you guys see here in my stream, it will be in the VOD content, even if it gets broken up. I don't know if Dr. Stefan's in here. So, flooded canyons. This is what this is showing. And Titan has seasons. It's a moon, guys. It's a moon. This whole time we're looking for things, you know, on planets. Guess what? It could be on moons. I'm here. So yeah, if he can bring up the chat, that would be great. And guys, Horizon Science right there, Horizon Sci. Can I get a shout out for him, please? Actually, just do Stefan. He is also a science streamer. We will be on a panel at TwitchCon. I owe the world to him. He's very patient with me. Moons with atmospheres, I know. And they even get heated up. So guys, a lot of where my science stream has gone, I owe to this man. He'll be on here with us. So, it's 6 o'clock on the dot. For mod. That'd be like an honorary one. I have a lot of honorary mods, but I love them. Fingers crossed, this should be great. I think it will. So I'm ready when you are. Let me know. I do have a message from him, Dr. Stefan. If you need my help with anything. Excellencias, thank you for your sub, buddy. Yeah, so it is half off subs, guys, from now until what, October 2nd? So if you want to pay $2.50, even if you only support it for a month, which I understand a lot of people will with this whole thing that Twitch is pulling, I'm okay with that. You help me with science and booby streaming. So just so you know, it's a hangout, Dr. Stefan. Hangout invite. So yeah, $2.50 for booby science streamer. And then I just get a response from Visions. I think Visions just woke up. I know. But think about if she was like, physics, guys. Mind blown. It's okay. We're not here to talk shit necessarily. It's okay, guys. I can kind of do that. I mean, shit, a lot of things would be easier. I wouldn't have to sit here and research stuff. I wouldn't have to paint horrible models of the solar system. Hey, to each their own, though, right? You blind me with science. That didn't sound right, Hammerfall, but it's fine. I'm fine. I understand, dude. I get it. I'm not jealous. I like science. Hey, Defier. Welcome back. Stealth. Hey, you. So, I don't know. Dr. Stefan, did you hear me? I said I have a Google Hangout invite from him. He's like, hi, this is Jason from University of Idaho. He's really funny, guys. He's got a sense of humor. So I know I'm a little bit different. Almost there. You're fine. Take your time. You're good. You're good. Don't worry about it. And also make sure he can pull up the stream ahead of time. Proteus, that's not the $2.50. You misclicked. Can I get some real Hail Sagans up in the channel for Proteus Black, guys? When I first started streaming, I was playing an MMO RPG, and I would do this on the side. I'd go to space every now and again. I needed the chat flooded for him, please, please, because he was like, people are gonna like space, and I'm like, whatever. Nobody wants to learn on Twitch. He's like, keep it up. Here, I'll make you an actual thing with all the controls you need for Space Engine. What MMO? EverQuest. Yeah. But he kept me going and was like, no, I think you got something here. He's been around for over a year now. He was like, no, people are going to like this. And I'm like, I don't think so. This is a gaming website. And then they were like, hey, creative. We're opening a creative section. And I was like, okay, all right. They're like, IRL. I'm like, all right, now I have no fucking excuse. So he's amazing. So yes, Proteus, thank you. And then he moved across the pond too. And I was waiting for him to come back because he really did push me. So Proteus, thank you for the tier 3 sub. From the bottom of my heart. I appreciate the hell out of you. Here's my water amino acid. It's not G Fuel. So guys, Proteus, amazing man. And yeah, he's a music teacher, but he likes space too. It's weird. They kind of go together. A little bit, you know. Here's some real images from Cassini with my logo. Sky Fuel. I bought one thing of G Fuel. I want to try it, but they're gonna have to sponsor me in science. Yeah, no, I'm not even lying. Invitation? Where? I don't see it. Oh, there it is. I got it. So these are real images from Cassini, guys. I'm gonna kick out the window. Hey, careful with that hammerfall. People are sensitive. Very sensitive. So when the interview is done, I'm not done with you guys. You hear me? We're on. I sent the invitation. Oh, there it is. All right, guys, ready? Let's do this.
Three, two, one.
There we go.
Sorry, we just woke up my chat. My chat is fully awake now. I just scared them, but we're good. Sorry, chat.
So Jason, I'm going to send you a message where you can follow the chat.
Okay.
What you want to do is to mute when the window comes up. You'll want to mute it so that because there's a delay between.
Okay. Yeah. I'll probably bring it up on my other computer here that has no sound on, so that would hopefully.
And hello,
address
Dr.
the problem.
Barnes.
Hi.
Everybody, this is Dr. Barnes, Associate Professor at the University of Idaho. And I while he's doing that, I can tell you a little bit about him. Also, you guys can type !guest. He graduated with his Bachelor of Science in 1998 from Caltech. So, you know, not a great school. And it's an awesome school. University wise, one of the best, especially for this kind of stuff. And then he got his PhD from the University of Arizona in planetary science. So, he is here. Can you guys see him on my screen? Yeah, I know it's a little, see, he's waving. Chat pop out. What equals what? So here he is. And yeah, guys, this is a different thing for most people in the university. So we're glad to have him here. And by the way, so Joe Hudson says real quick, as you're configuring things, Dr. Barnes, he says, by the way, when I researched you, you look like a very cool guy. I might have slipped in.
Looks can be deceiving.
Hey guys, he shaved today.
Just for you.
just for all of you guys here in chat. I told you he's funny. He's got a sense of humor. It's great. But yeah, whenever you're ready, take your time. No pressure. Don't worry. This is Twitch. We are pretty go with the flow. So
I think are we good?
Yeah, I'm set up. I can see. I see the incoming stuff. So.
All right.
Awesome.
Well, thanks for coming on.
Yes, thank you.
How's Moscow? Is it time for the Lionel Hampton Jazz Festival?
That's in February.
February. What a great time to visit Moscow, Idaho.
Well, that's the idea is to, the hotels are real open then otherwise. So, no, it's not quite as smoky as it has been here. We've been having these fires up in the Northwest. It's been pretty brutal.
Yeah, it actually,
Uh,
when we talked with Emily Levesque, she said that there was a lot of smoke in the Puget Sound area that went over the
yeah,
top of the Cascades.
absolutely. It's over there. It's in British Columbia, Canada, and down in Utah and Northern California. It's really bad. So
Yeah, here in
better
Colorado,
now, better today than it has been though. So that's a good thing.
yeah, we have it too. We got it from you guys, but we also have our own fire issues. So it just compounds.
Native.
Yeah, right. So, but it makes the moon look really cool at night. So, I'm okay with that. So I guess to get right to it, I've been doing a little bit of prep.
Yeah.
Yesterday, I did a little bit of prep regarding the Cassini mission. I know your focus, and please correct me if I'm wrong, is mostly exoplanets, right? And that's how you know Dr. Stefan here?
Yep. No, actually, about half my research is solar system and half exoplanets. So.
Oh, okay. All right. And so
I straddle the community.
Yeah, that's perfect. And so your focus with our solar system, well, at least I'm looking at some of your publications that you have been a part of a team on. You've got a lot. Very impressive, I got to say. I looked at Google Scholar and I was like, okay, I there's so many here. But it is mostly with Titan.
Yeah.
Which is one of Saturn's moons, guys. You guys know that. And would you want to, how did you get into working with this stuff in the first place? That's usually what I ask people right out the gate. So astronomy.
Yeah. Well, as far as the Titan work goes, so when I was looking for something to do my PhD on, I was like, yeah, I'd love to do something interesting in the solar system. But the sort of rule of thumb for us is never work on a mission before it starts returning data. So I started graduate school in 1998, and Cassini had only launched in 97 and didn't arrive at Saturn until 2004. I have some unfortunate colleagues that did not follow this advice and worked for Mars Polar Lander, for instance, in the year 99 and 2000. That this is the one that crashed into Mars. Its companion was crashed because of the metric imperial conversion factor problem, but this one failed because of inadequate testing. And all the people that had worked on that, right, weren't able to get any PhDs out of it. So there wasn't anything returning data at the time. And so I was working on exoplanets for my PhD. But after I graduated, my now wife, then girlfriend, hadn't graduated yet, and so I was looking for something to do around University of Arizona for a couple of years, and Cassini was just arriving, so the time really worked out well for me, and that I just started working on Cassini data right as we arrived at Saturn and right as the fire hose opened up.
And yeah, we just watched a documentary on Titan alone. It was a pretty good one about the whole mission of not just Cassini, but the Huygens probe, which was attached to it. So when did you actually enter in that whole thing with Cassini?
So it's basically, I think my official start date was July 1st of 2004 on my postdoc for Cassini, and that is the day that of arrival. We arrived just right around then. Was Saturn orbit insertion burn. I sort of swooped in right at the last second there, but it worked out very well for me because at the time of launch, or at the time actually that the instrument I work with, the visual infrared mapping spectrometer, was designed in 1989, people hadn't realized it was going to be able to see the surface of Titan. So the team was sort of selected among people that were looking at other icy worlds, Iapetus in particular. And so there was sort of a niche in the team that wasn't being filled, and that no one had signed up for looking at for Titan. So, and there was a whole scads of things to do there. So it really worked out well for me in terms of placement right when I got in.
Awesome. And so tell us a little bit about Titan, just layman's terms. If nobody knows anything about Titan, what is Titan? What's cool about it? And where did you come in with that?
Yeah, sure. Well, Titan is the second largest moon in the solar system. It's quite a bit larger than our own moon by about 50% in terms of its radius. And what really sets it apart from everywhere else is that it's the only moon with a thick atmosphere. So if you think about it, there's only 4 places in the whole solar system, in the whole universe we know of, that have both solid surfaces and thick atmospheres. So there's the giant planets, right, that have thick atmospheres, but it's just gas and supercritical fluid all the way down, so there's no surface. There's lots of places like the moon and Mercury with solid surfaces but no atmosphere. But among places in the solar system that have both the solid surface and the atmosphere, like we do here on Earth, it's just Venus, Mars, and Titan. And Titan, of these 3, Titan's atmosphere is the most like Earth's. Its pressure, the surface pressure at the surface of Titan is only 50% higher than ours, so it's about 1.5 bars. Compare this to Venus, right, where the pressure is 100 times thicker than our atmosphere, and Mars, where it's 100 times thinner. So off by 50% doesn't sound so so close, but when you look, you're talking astronomical numbers and orders of magnitude, it's not bad. Furthermore, Titan's atmosphere is made of the same thing ours is mostly made of, which is, does anybody know what's our atmosphere mostly made out of?
Yeah, I want to know. Chat, does anybody look at this? Look at this.
I thought
What
it was
a
rain,
pro.
apples, and small rocks.
Well, if you have kids, maybe.
No, so that's actually
our atmosphere is mostly made of nitrogen gas, right? N2. It's about 70% of Earth's atmosphere is nitrogen gas.
Look at that. Do you see chat real quick?
And
Do you see chat? So there's about a 30-second stream delay.
It's coming up. There you
yeah,
go.
No, there's a delay. Hey, you're used to delays with data or data.
So I'll have to program that in. I was trying to get some participation.
Look at that. Everybody's doing great. I'm so proud of you guys. Okay, go on. Sorry.
So Titan's atmosphere is actually made of the same thing. It's mostly nitrogen, 95% nitrogen. Of course, out at Saturn's distance from the sun, 10 times further from the sun than Earth is, it's a hell of a lot colder. So out there, the average temperature is about 90 degrees Kelvin, right? So this is the absolute temperature scale, whereas it's about 300 degrees Kelvin here on Earth. It's about 90 degrees Kelvin there on Titan. Recall, liquid nitrogen is 77 degrees Kelvin. So we're well above the liquid, the point where nitrogen would boil. So we can't have liquid nitrogen on the surface. But the nitrogen there is a gas in the atmosphere. And the other cool thing about Titan is it's the only place in the universe that we know of, other than Earth, where there's liquids sitting out on the surface. As I said, liquid nitrogen isn't stable on the surface because it's too hot. But it turns out liquid methane, CH4, and liquid ethane, C2H6, are both stable on the surface. If you pour out a cup of liquid onto the surface of these liquids on the surface of Titan, they'll stick around. And we found that near Titan's north and south poles, there are giant seas and lakes of liquid methane, hundreds of meters deep. And when this stuff evaporates, it makes clouds that create rain and carve channels, just like we see on Earth. So it's rain of liquid methane instead of liquid water, but it really leads to a very similar surface geology than we see to Earth, and a more similar surface geology than any other planet that we know of yet.
Yeah, and I have a picture up on my stream right now of that topography. And are these mountains? And this could be wrong because I've heard that the lakes are found more on the northern and southern hemispheres.
Right. So this is something we should have been able to figure. One of those things that should have been obvious, but is only obvious in retrospect, right?
Mm-hmm.
On Earth, we have ice caps at the poles because that's the coldest part of the Earth. On Titan, the lakes are at the north and south poles because those are the cold traps. Those are the coldest parts, and therefore, when liquid condenses there, it's harder to evaporate, where if it condenses near the equator, it evaporates, goes around, and then eventually rains on the pole and sticks there. So they're the cold traps at the north and south pole. So we see these expansive surface liquids there at the north and south pole, mostly at the North Pole, actually, which is interesting because you'd think it would be even, but we don't see it that way. And so mostly within 25 or 30 degrees of the North Pole, there are 3 very large seas called Kraken Mare, Punga Mare, and Ligeia Mare. And these are really big, not quite maybe big enough to call oceans, but certainly much larger than any just natural lake on Earth.
Interesting. So we see more at a certain pole, and what does that mean? So what did that tell you guys as scientists, that you're seeing more of a?
Well, we don't know. So if you know, let me know, and we'll write a paper.
Sounds good.
It's been suggested that it might be related to Milankovitch cycles, which are the same sort of variations in orbital characteristics, so orbital eccentricity and location of the seasons, and orbital obliquity, or the planet's tilt. So on Earth, those vary kind of only by a little bit, but it's just enough to toss us between glaciated states like we were in 20,000 years ago and interglacials like we are in today. So they thought there's been a suggestion that maybe these variations have led to why we have liquids at the North Pole today, and that in 100,000, 200,000 years, you might see it flip to the other side. That's an idea, but it's not really obvious, if you ask me, why the liquids are so predominant in the North and not in the South today.
And where do you guys come up with these names? I heard you use.
I wish we came up with them. Unfortunately, the naming is left to the International Astronomical Union.
Okay.
Oh, these are the same people that demoted Pluto, right?
I was about to say the same
So
people that ruined
humorless.
Pluto.
Yeah, I don't know. So, let's see, the lakes are named after sea monsters, mythical sea monsters. I have been involved in naming some things and trying to establish some different name categories, and we have gotten some cool names. Let's see, the hills on Titan are named after characters in Middle Earth. The mountains on Titan are named after mountains in Middle Earth, the Tolkien series. So we actually have a Doom Mons, which we think is a giant volcano, possibly on the surface of Titan. And then there's some, less cool names, like the lakes on Titan are named after lakes on Earth, thereby to maximize the chance that you will get them confused. So there's hits and misses with the IAU, and they're. I definitely understand why we want to have a single group that decides what all the names are and how things are named, so that we all can interconnect and talk about different places and know what we're talking about. But it's definitely a painful process of getting the names actually, getting individual objects named. So someone said, I think we do have a Misty Montes somewhere. I forget which one. That might be one of the interesting sets of linear mountain chains. I'd have to look up exactly which one it is.
Yeah, and feel free to actually, this isn't anything formal. I want you to feel pretty comfortable. So if you want to, look something up and then send it in the, Google chat window, I can bring it up here too as well. So it's pretty
all right,
relaxed.
Let me try that. I'll see.
Yeah, it's a nice atmosphere. This is a nice thing about Twitch. So yeah, we got some Tolkien going on, guys. And, so yeah, the IAU, from what I understand, there's not a lot of planetary scientists. That's one of Alan Stern's.
There are some.
There's
the
some
ones that are involved definitely are the ones that help, right? So there are several planetary scientists, Rosalie Lopez and Zibby Turtle in particular, that are there trying to coordinate things. But it's definitely not all.
Right.
Planetary science. It's mostly planetary science makes up maybe 10 or 20% of the IAU. So you're right. It's mostly people looking at galaxies and high Z quasars and stuff like that, and they're like, oh, what are this planet stuff? So sometimes we do have to sort of educate them about what the latest discoveries are, because they don't know.
Right. But there's a few points on Pluto, guys, that we've talked about. The ability to clear out its neighborhood is kind of significant. So. But still, it is a very interesting dwarf planet. So it's good. Anyways, so
Jason, I have a question.
Oh, there we go.
Did you? Yeah, go for
it. You joined Cassini officially through the guest investigator or the participating scientist program, didn't you?
Right. So as far as involving young people in Cassini, it's sort of a red button issue. In order to be a full member of the Cassini team, you had to apply in 1989. My affiliation of Parkway Central Junior High School evidently was not good enough for them. They did not select me at that point. But the only other time there's been to become an official team member was on the participating scientist call. And I became an official member as of the participating scientist call in, what is it, 2012, 2011, something like that. But yeah, it's definitely something we're learning, is that there needs to be some mechanism for bringing young people into a mission, especially if it's a 30-year-long mission to the outer solar system. You got to think ahead.
That was how I ended up joining on Kepler. It did take us a while to elbow in on our status in terms of like becoming full members of the team. And I know that it took some lessons, because I think Bill Cochran was on Kepler and his wife was on Cassini, I believe, from Texas.
Yeah, Anita, I'm not sure I don't think she's on Cassini, but she's on plenty of planetary missions. Yeah. Okay. Yeah, so actually the participating scientist is something that from the planetary world that astrophysics really doesn't do. But since Kepler was initially chosen under the Planetary Discovery Program, you guys sort of had this participating scientist program built in. And a lot of the astrophysics people were like, what is this? I don't even know what to do with this. They just didn't get it. But what did you think? Was it a useful and interesting way to be involved on the team? I know it has issues, but I think it's better than than nothing.
I think the best people to ask. I can tell you the reports that I got from people who were on the team for a long time.
Okay.
And that was that bringing in a generation of scientists who kind of were weaned on the Sloan survey. So Sloan was wide open in terms of like the team communicated with each other very well. It was well organized, so people could work on science and kind of carve out their niche, and everyone knew what everyone else was doing, and they knew like how not to step on toes and stuff like that. And so there was a group of us that joined Kepler because Kepler was mildly dysfunctional in terms of how it was structured.
Really?
Yeah.
I didn't think that. I thought it was definitely not mild. It was severe.
Okay, I'll let you say that.
Because he's no better, by the way. I'm not.
No, okay, so I was being a little bit polite, but
yeah, you're good. This is Twitch.
So
no, you're fine. No, you're fine.
Basically, we're saying, look, headquarters is paying for us, and we can't do what they're asking if we don't have better communication. And in fact, so I'm writing a paper right now where Jason and I both know Jack Lissauer. He's a guy at NASA who's on like almost everything that's ever been done that's important. He's got his fingers on somehow. So I'm working on a paper with Jack where we're revisiting some of the early Kepler discoveries. So I've gone back to my emails from 2010.
Yeah.
And I'm reliving all of the trauma of trying to get access to the data and get onto the telephone calls where, people were saying, oh, there's so much to do. There's so much to do. And we're like, we'd like to help, but no one's giving us a phone number to call.
Yep. So I have to say that, so I joined Kepler in 2007, first half of 2008, I was a postdoc for them. And, there were several, science team meetings where I said, look, hey, I'm on Cassini. Here's what we learned is that there are so many data out there that very quickly initially everyone's like, no, this is my data. No one can have it. But I'm like, it becomes painfully obvious really fast that that's the exact wrong strategy. The proper strategy is we have so much to do. And we just, if people are out there and willing to help, we should just pump the data out to whoever can help and maximize the impact of the mission and the science results from the mission by getting the data out to everybody.
Yeah.
And they were like, no one listened to me. I was just a kid. It's fine. But it took them many years to figure out. And it was their second extended mission where they realized, oh, geez, we're not going to get this extended mission unless we make the data public to everyone right now.
Yeah.
So eventually they got the hint, but it took a really long time. Do you remember how ridiculously protective they were of the data? They decided they were afraid someone was going to like hack into their computers and steal the data and like analyze it without.
So that's actually, they moved the data it used to be that they were going to run everything out of Ames, and they
Right.
had to move it to JPL. So a bit of history is that JPL as an institution predates NASA as an agency, and so JPL has a different set of rules compared to other NASA facilities like Ames and Goddard and Johnson and Kennedy and all those ones. So JPL operates under different restrictions, and so the Kepler mission had to host the Kepler data out of JPL instead of hosting it out of Ames, to get around some of that stuff. But I remember this one email that I had where the person said, "Well, just tell me what data you want, and we'll send it to you." And it was like, "Well, how do we know what data we want until we've looked at it?"
They had a rule where, like, once you downloaded the data, you had to encrypt your hard drive so that, like, no one could.
My key fob and everything. It was.
Who does that?
Right.
That is so ridiculous.
Yeah, and I've heard this. I've heard this, and actually, Dr. Stefan and I have talked about it a few times because this gives so much to conspiracy theorists, where they're like they're withholding data or data, singular, plural, and then they think, well, what else are they hiding? They want it. They want it shared. I promise. Everybody wants this, except certain people. But yeah, no, that's.
Yeah. Well, I mean, the people on the team have a legitimate concern. Their concern is, well, I spent 20 years, 10 years developing this spacecraft. I should get first cut at the data. But what it really comes down to is, if you make all the data public from the get-go, if the team writes a paper, that carries a whole lot more weight than Joe Schmo at University of Idaho writing a paper, So it's not like it really inhibits you, I don't think, is the team. The team still has primacy. Everyone still is going to recognize a team paper first. And so it really doesn't make sense to have this sort of proprietary period.
So I didn't mind the proprietary periods so much as I minded that.
As long as you were in on it.
Well, but it only lasted for like a year, because that was Sloan's model too. Was Sloan will keep it proprietary for 1 year and then we'll release it after 1 year, and it didn't really slow anybody down. I remember there was a big brouhaha because of a 6-month delay, and it's like, well, no one was ready to take the data.
Oh yeah, that was.
The funny thing is, maybe I shouldn't say this out loud, but I was the one that wrote the document that outlined how I wrote the policy.
Great for the extra 6-month extension.
Yeah, for the ones, but even within the team, it was totally cloak and dagger. Like, if you give me the right handshake, then I'll let you see a scanned copy of a PDF of a picture that someone took with their cell phone, and you can.
Yeah. So I mean, it is really hard to develop the right team chemistry. Mm-hmm. And so I've been recently on a new proposal for a new Titan mission. And one of the things we are going to have is the data are going to be public from the get-go. But yeah, I realize that, especially on a competed mission like Kepler, I always thought, gosh, why don't they pick the nicest group of people that's going to get the most done and work well together? But then you realize that you actually have to pick your team for different reasons. Like, oh, gee, this guy's my competition. If I don't put him on my team, he's going to start his own team and compete with me. So you got to have that person on there. And, this woman represents that, institution. We have to have someone at, JPL involved or whatever, right? So the team chemistry actually did not play into it at all, whereas I thought that should have been important. But the point is, you write the proposal with the team that's going to get the proposal won, and
then you bring on the participating scientists to actually make it work.
You worry about how you're going to actually do the mission 10 years later.
And a lot of people don't know this. This is actually pretty interesting information. Just like, I don't know if you guys know, chat. This is pretty cool stuff, and there's a lot of people that develop conspiracies with this kind of stuff, withholding data, whatever, data. But yeah, and this is why we like Twitch, is because you can kind of casually talk about this. But yeah, yep. And Inertia says, got to get that money. But yeah,
it's expensive.
It is.
This is, I mean, NASA is very generously funded by you, the American taxpayer. But it's hard to do stuff in space, right? Mm-hmm. You got to design something that's going to work in an exotic environment. And then you're going to launch it off, and it has got to work the first time.
Yeah, Hubble
You can't
saw
send
that
someone
issue.
up there and like
Yeah.
with a wrench and fix it.
So since it's getting close to the end of the mission, if you were to list, I don't know, like a top 10 big Cassini discoveries, what would they be? And also, if you have pictures of this stuff, you could.
Well, I have one on my screen right now. It's the one he sent. I'm imagining this has some pretty good importance. Yeah.
Well, I mean, that one's the Misty Monte. So I'll talk about that one. That's a radar image of Titan. So Titan's thick atmosphere makes it really exciting, but it actually also fills it with haze particles that make it really hard to see the surface. So you either have to look in the infrared like I do or use a radar to see down to the surface. So it's really kind of weird to interpret radar images there, but sort of the crinkly looking stuff that you're seeing are a set of mountains that are about several hundred meters to a kilometer high on Titan. And we're seeing them from the side, so they sort of show a little bit of structure. But these mountains are pretty cool, actually, on Titan. We see these mountain chains on Titan that are long, linear mountain chains, which, the Rocky Mountains and the Andes are all linear mountain chains on Earth. But that is really weird on other planets. That does not happen anywhere but here. Mm-hmm. We get these long linear mountains here because of plate tectonics, which doesn't happen anywhere else that we've looked. So we're not sure what forms these really cool linear mountain chains on Titan, and they're sort of really unexpected and unusual. I wouldn't necessarily call that one of our top 10 discoveries, though. I mean, certainly the Enceladus plumes. So Enceladus is a tiny moon, only 500 kilometers across, that appears to be volcanically active. It's actively spewing water ice out of its south pole today. And the Cassini flew through these plumes several times and took images of where they came from. This is definitely a really exciting fundamental discovery that Cassini has made. Let's see, it's hard to come up with a top 10 on the spot. Certainly at Titan, the discovery of the lakes and seas was in the top 10 of the whole mission, and possibly even Titan's sand dunes as well. Titan's equator is dry. The lakes are at the poles. All the equator is dry and covered for the most part in giant sand dunes that are 100 meters high and hundreds of kilometers long, and they cover 20% of Titan. So I like to make fun of my Mars colleagues that think they're the desert planet, because Titan has them beat. Not only does it have a lake district, it also has a huge expanse of sand dunes, active sand dune desert terrain. Certainly the Huygens landing and where it landed, right on Titan there, where you can see canyons and rounded rocks. Here, let me see if I can find some Huygens landing images, although I'm sure you guys could find these just as well.
Yeah, I could find them for you. You can keep talking about it. I got you.
Okay. All right. Yeah, because that's an easy one to find. So that's really exciting, actually, to be able to land on the surface of Titan and see what it looks like. We haven't landed all that many places, folks. It's, the moon, Venus, Mars, and this comet that the Europeans landed on. That's it. And so, the only moon that's been landed on in our solar system other than ours is Titan. And it's that thick atmosphere that makes it possible. Landing on Titan is actually pretty easy. If you have a heat shield, you just punch through, and that slows you down. You just need a parachute to be able to land.
Yeah, a lot of people wondered if this was CGI. What you're seeing right here.
Well, I can't actually see what the specific image you've pulled up, so I can't answer that. But let me see if I can get on my phone the Twitch stream. Unfortunately, I run a rogue operating system, FreeBSD, which is for people that think Linux is too mainstream, I guess. So I actually can't run the well, maybe I can. No, I need Flash. I don't have Flash installed on here. Let me see if I can get on my phone.
Yeah, this one actually includes the bounce of when it lands too.
That one is CGI, but it's
But I don't think this part is right here. I think these are images that were pieced together because
it's generated from real data,
mm-hmm.
in combination with the telemetry from where the spacecraft was and what its orientation had been. Yeah, this is CGI, but it's mixing and sort of an active mix of actual images and mapped terrain put together with what we know of how the trajectory was as we came down.
Yeah, because you can kind of see
it's
that.
Pretty spectacular.
It is. It's super cool. It does go on, quite a bit. Then they show the rocks that it lands in front of. And those rocks, what are those rocks made out of?
Those rocks are made out of water ice. So you go down to 90 degrees Kelvin, water ice is absolutely hard as a rock. So there's no problem just making those just hold up. And most of the crust is made of water ice, and a lot of the volume actually of the whole moon is made of water ice. Water ice is super common in the universe. Right, the number one most common element in the whole universe is hydrogen, of course, what the sun is made of. Number 2 is helium. Number 3 is oxygen. So if you take that oxygen and it's trying to combine with something, the most common thing it finds is hydrogen, create water. So there's water all over the place. And most of Titan, by volume, is actually made up of water. And that's what those little rocks are that you see. They're about the size of your fist.
Right. And so why is water ice? I mean, why is that? I mean, everybody would probably get really excited because I think that's what happens a lot when we discover things in our solar system. They're like, oh my God, it's water ice. Why is that for people involved in astronomy or astrophysics or planetary science, which is, again, I'm just being very general in those terms. Why is water ice not as exciting as a liquid?
Yeah, because water is everywhere. People wonder, why did Earth's water come from? The question is, where did it go?
Right.
If you just took an average clump of universe material and drove off the hydrogen and helium, it'd be mostly water.
Mm-hmm.
So without hydrogen and helium, in fact, if you look at the giant planets of Uranus and Neptune, those planets are mostly made of water. They're about 10 Earth masses of water with a little bit of hydrogen on the top. And so once you get far enough out in the solar system that water doesn't vaporize once it freezes, you can build planets out of them, and it's just all over the place.
Right, and the time that it does vaporize is if it's on an orbital path around the sun.
Yeah, if it gets too close, then it'll vaporize. So in the inner solar system is unusually water poor, but everywhere else there's water everywhere.
Right.
So what about things related to the planet itself? I remember seeing someone from Cassini give a colloquium when I was in graduate school, and the thing that the picture that struck me the most was the one that has Saturn with the rings edge on, and the rings are 1 pixel.
Saturn's rings are they're ridiculous, right? You think about it, they're like 20 Earth masses across in their total dimension, yet they're less than 10 meters thick. The collisions between them keep them so tightly in that in Saturn's equatorial plane. It's ridiculous. And so we were able, I think the coolest part of the ring plane crossing, when the sun was coming directly on the rings, is that you were able to see 3-dimensional undulations in the wings. They might only be 10 meters thick, but there are places where they warp up and down up to a kilometer. You can't see that very well when the sun's coming directly on them, but when it's coming from the side, you could totally see this topography within the rings. It was really cool. In terms of the planet itself, there's the rediscovery maybe of the North Polar hexagon. Turns out at Saturn's North Pole, the clouds all organize themselves in a giant hexagon, like a big bolt head at the North Pole of the planet. And we saw this big, giant storm system develop in about 2011, I think it was. Huge, like half an Earth across. And this huge thunderstorm, it was a water thunderstorm down below the clouds. And it was so big, it lasted for months and months until it actually went all the way around the planet and got back to where it started at. And that's when it sort of died out. But we do see these sort of cloudburst storms on Saturn from Earth. You see them every 30 or 40 years. So we were really lucky to be able to grab it from Cassini and see the whole thing develop in high resolution.
Yeah, and that hexagon was a pretty big mystery for a while, wasn't it?
Cool.
It's so cool. I'm showing everybody right now. It's super, super cool. I've always been fascinated with it. But yeah, and this is only on one pole, right? That there's this hexagonal shape, right?
Right. So what's weird is, we can come up with reasons why you'd have a hexagon, but why would you just have a hexagon at the North Pole?
Right.
Why don't you have one at the
South
Pole?
Is this?
We don't know that part. We don't know yet.
Where's this
but
favoritism?
It seems to have to do with, the way that the individual, it's like a giant jet stream near the North Pole that happens to wander back and forth in latitude, just such that it goes around 6 times in a single circle of latitude around the planet.
Interesting. And so did you do any work with like seasons? Because I have this really cool image up of it has seasons.
Yeah. So I mean, I'm mostly working at Titan, of course, but
right. Well, yeah. Titan's seasons. I have an image.
Because we're so far from the sun, a single Titan year takes 28 Earth years. So it's a long time.
Do the math,
so
guys.
That's one of the reasons. Sorry, go ahead.
Oh no, I was just saying, do the math, guys. So 28 years.
Yeah. So I'm only one, so that's good. But it means I can't drink yet, so that's the downside. But because of that, we arrived in 2004 in South Polar summer, and we spent the last 14 years getting up toward the start of North Polar summer. And so by extending the Cassini mission as we have for that full 14 years, we're able to see one full seasonal cycle as things shift from south to north. Summer shifts from south to north. And for instance, this is something that we haven't gotten published yet. We've submitted, but it's not out yet. Turns out right around the equinox, which must have been northern spring, all the thunderstorms kind of moved past the equator, and they actually generated these giant dust storms similar to the ones we see on Mars, but they were sort of localized, but many hundreds of kilometers across, just by the winds of the atmosphere shifting as we went from South Polar summer to North Polar summer. And we saw a bunch of clouds and thunderstorms raining at the South Pole when you arrived, and so we expected, once North Polar summer comes, we'll see a bunch of storms at the North Pole.
And so
we're still waiting.
We see, obviously, there's a bit of an axis tilt here.
Titan's and Saturn's axis tilt is about 26 degrees. It's just a little more than Earth's, basically
a little bit
the
more.
Same.
Okay. And then I'm looking at this too. This says a nice thing about exactly what you were talking about there. The equinox here being in 2009. How fast does Titan rotate? On its own axis?
Right. Good question. So Titan takes 16 days to go around Saturn.
Mm-hmm.
And like our moon, it's tidally locked. So it spins once per orbit. The tides keep one hemisphere constantly pointed towards Saturn as it goes around. So it takes 16 days to go around Saturn. And so the rotation is so slow that the Coriolis effect is small, and you don't develop these cyclonic storms like people in Florida have just experienced.
Mm-hmm.
So that kind of thing doesn't happen on Titan just because it's rotating so slowly.
Interesting. And so they okay, so obviously we everybody here knows kind of, something being tidally locked. Our moon is tidally locked to us. And I guess, how does that have an impact on how this, what I'm curious about is what are the theories behind Titan? Because we don't have these kind of moons, I mean, with such a beautiful atmosphere like this, say around Jupiter.
Right.
Jupiter doesn't have these nice atmospheric rich moons.
Absolutely. Great question. If you figure it out, let me know. We'll tell everybody. It's not at all obvious what sets Titan apart. Ganymede is even larger around Jupiter,
Mm-hmm.
has no trace of an atmosphere at all. Callisto and Europa and Io around Jupiter, all huge,
Mm-hmm.
very massive satellites, no atmospheres at all. It's just not clear why Titan is different. One rather aggressive idea is that maybe Titan isn't a primary satellite. It wasn't formed at the same time Saturn was. So that's sort of like, whoa. To us,
Yeah.
to us planetary scientists. we assume, we've slowly pieced together that everything in the solar system formed at the same time. And this has been it took us a long time to realize this, right? That the moon formed only 100 million years after the formation of the sun and the protoplanetary disk. All the planets were all born at that same time. Jupiter's moons were all formed at that. All the asteroids were born at that time. All the meteors we see. The Saturn system is different. Maybe the Saturn system is sort of a second generation satellite system that was formed by the breakup of a previous one. And maybe the rings have something to do with this in terms of creating new moonlets as they slowly spread outward. And so we don't know if this is true or not, but that's sort of an aggressive idea as to why that might be happening. But the real bottom line is we just don't know what sets Titan apart and why it's able to support this atmosphere, whereas just other moons just as big as it is, for some reason, don't have one.
Right.
I think that.
Sorry. Go ahead, Dr. Stefan.
So, because Saturn formed, what's the history of Saturn's position in the solar system?
I was just going to ask that.
Yeah. Well, we don't know that either, but we're starting to recognize that planets, they don't stay where you put them, right? It used to be we'd go through planet formation models on the computers and try to come up with a system that looks just like our solar system. And we couldn't do it. And they're like, wow, what's going on? There must be something weird to allow Uranus to form that far from the sun, because we can't get it to work in our models. And now we know that there's a reason for that. It's that Uranus didn't form out there. Uranus formed probably between Jupiter and Saturn and was flung out and had its orbit circularized later. Saturn itself probably formed interior to where it is today, migrated in for a while until it hit a resonance with Jupiter, and then was able to migrate outward to about where it had its present position, and it's had a little bit of evolution over the last couple billion years. But this is actually a really huge advance in planetary science in particular over the last 20 or 30 years, as we realized that planets where they are today is not necessarily where they started. And Pluto is a great example of this. Pluto initially must have formed much closer in to the sun, and was actually captured in a orbital resonance by Neptune and pushed out as Neptune itself moved outward from 20 to 30 astronomical units over in the early solar system. It was essentially snow plowing and pushing Pluto out with it. And so Pluto and a lot of its buddies out there in the Kuiper Belt actually aren't where they started either. So this is actually a pretty exciting development, I think, for us.
Yeah, and I was talking about that with a lot of people in here because, as you both are part of the Kepler mission, or you were, and your work there, a lot of the things that we started seeing first were transits of hot Jupiters being very close to their host star. So, like you said, we're trying to match our solar system to ones that are being observed and found now. And these hot Jupiters are very close to their star. And we're looking at our solar system. We're like, this guy's 5 AU out, which guy's 93 million miles, 1 AU. And this is 5 times that distance. Yeah. It's weird.
For a long time, we looked at our solar system and said, oh, this is what a solar system looks like.
Yeah.
How do we form these?
Yeah.
And it's really shows you the danger of, extrapolating to an entire universe of 10 to the 22 different stars with an N of 1, looking at our own solar system. The type of different solar systems we found with Kepler is just awesome in every sense of the word. How you get not only different configurations, but configurations we thought were completely impossible turns out are just totally commonplace and just happen all over. So while our solar system type is not unusual, probably maybe 20 to 50% of solar systems may look like ours, with giant planets on the outside and nice rocky planets on the inside. We're not the majority, and we're not typical, I would say. There's a lot of these planets out there with close to their stars and other exotic configurations of eccentric planets and tilted planets. And it turns out the most common size planet in the galaxy is stuff that's about the size of Uranus and Neptune.
Yeah,
3 or 4 Earth radii across.
Mm-hmm.
Yeah. What's interesting about that is because Uranus and Neptune are like on the high end of it.
Mm-hmm.
When you look at the Kepler results, it's the most common size planet that we see from the Kepler results is a size that is not seen in the solar system. It's between Earth and Neptune.
So we have this huge gap, right, in between stuff that's one Earth mass and Jupiter and Uranus and Neptune that are 15 Earth masses. And so we thought that was because there are two types of planets, small rocky planets and big giant planets. Nope, turns out most planets in the universe are actually between that, and we have no idea what's going on with those things.
Yeah, and they're all right next to the star, where we don't have any of our own planets.
Where they obviously couldn't form.
Right. And so...
so this picture you're showing here is actually one I made with my instrument, with the visual and infrared mapping spectrometer instrument.
You're responsible for this guy?
I made that. So that is showing a sort of a picture of Titan from orbit as it's seen from our near infrared camera.
Okay.
And so you see the brown stuff near the middle there. That's the equator.
Okay.
And that brown stuff are all the sand dunes I told you about. All that brown stuff down there are giant sand seas at Titan's equator. The sand seas aren't made of the same sand that you get on the beach here, though, which is silicon, SiO2. The dunes on Titan are all made of organic material. So think giant 100-meter high mountains of coffee grounds. The green stuff near the equator there is, we think, probably this water ice bedrock, though it must be coated with some sort of gook because it doesn't quite look like ice. You can in some places see little bits of blue on the surface. Those areas are enhanced in water ice. This particular view doesn't even show any of the lakes, which are all near the North Pole there, because they just don't happen to be in this. You can't see them from this particular angle.
Do you have a picture of the lakes that you could link?
Oh yes, sure. I can send you a picture of the lakes.
Because this is a very, someone just said like glass, but you there might be waves from what I read from some of your publications that you worked on, small waves.
Right.
Yeah.
Right. So we initially said, oh well, if these are liquid filled, then they should have waves. So we started looking at with the radar, and they were just utterly flat. Like we're talking flat to within millimeters over hundreds of kilometers. Got me worried. Like, they should definitely be waves at some level. If things are that flat, makes you think that maybe they're really made of molasses or something that's very viscous and so can't form waves. So I was actually kind of worried about it for a while. But it turns out as we got toward North Polar summer and the wind started to pick up at the north, we have started to see some wave activity on the giant seas near the North Pole.
So they're not like Slurpees?
Well, or the slushy or something, right? I was really worried when we weren't seeing waves that there was something about them that we were missing, right? That some essential element, maybe there was a bunch of stuff dissolved in them or a bunch of particulates suspended in them that were preventing the waves from forming. But eventually I was the first one to discover waves. We actually discovered them in specular reflection. So you can imagine if you're looking at a liquid or a mirror, you get light that just bounces directly off and comes straight out. And if you get a wet mirror or a rough mirror, you can imagine like frosted glass a little bit, you can tell how rough it is by how it reflects. So that's what we were able to use to figure out the existence of these waves on Punga Mare. And I was really excited because it turns out their average angle was 6 degrees. I'm like, 6 degrees, that's pretty high. These are probably pretty big. But we ran it through a computer model to simulate how big those waves are. And it turns out their amplitude is about 2 centimeters.
Yeah.
So,
pretty minuscule in terms of what we know. Right. But still cool nonetheless.
The first waves anywhere but Earth, right?
Right.
But they're kind of like ripples.
Yeah, everybody's like, we're ready to see some. I didn't know this was your image. I just pulled it up because it's a good image. So guys, that was not scripted. I promise. But yeah, so I'll talk to you guys a little bit about this real quick. So both of these scientists that we're talking to right now have done extensive work on the Kepler missions. So talking about exoplanets, things that we find outside of our solar system. A lot of that will be better understood with the help of the James Webb Space Telescope, which launches hopefully next year. And you know, that's going to allow a lot of the things we're going to learn is more about atmospheric composition, running the spectroscopy on things like that, and understanding what these exoplanets are actually made of. Right now, we can guesstimate with using things like mass and let's see real quick here. Okay, yeah, I really had no idea I was using your pictures because this looks pretty similar to. Oh, this is pretty. Guys, wait for it. Wait for it. Wait, okay. Dr. Stefan just ruined Christmas. He just dropped it in there, but there you go. There you go, guys. So tell us about this.
Okay, so this is another image that we made here at the University of Idaho that shows the North Pole, right? So in this one, you can see that giant, you know, sort of the big yellow spot over there. That's a specular reflection. That's a glint, a sun glint off of these liquid methane, ethane seas. And in fact, in particular, that one is Kraken Mare. And if you actually look, the dark areas here are all the major seas of Titan. So this big one here on the left there is Kraken Mare. The one sort of the upper right is Punga Mare. And then sort of near it's harder to see down near the bottom is Ligeia Mare. So this is a beautiful, almost cloudless day on Titan. That orange, the orange E looking thing over there, that is a cloud deck, a small set of thunderstorms that are propagating across the northern end of Ligeia Mare there. But if you look to the right of the yellow spot, within the dark region, you see that there's a little red splotch in there, and that turns out that's a set of waves. We haven't even published this yet. I keep meaning to, but I always have more papers to write. But that's another set of waves that we've actually seen in that location fairly often, as if maybe it's not caused by wind, but it might be caused by liquid being funneled through this channel back and forth as Titan's tides, pull the liquid back and forth within the sea. So that's a set of waves on Titan that we haven't even published yet. We got to get that out.
And wind speeds. I'm assuming that there's some of those.
So the speed you need to get winds of about 0.8 to 1 meter per second in order to really start initiating wave activity on Titan. And it turns out that's about the same limit that you need in order to be able to move particles in the sand dunes as well. And it seems like we actually don't get that level of waves very often, because most of Titan's seas don't show these kind of wave-like reflections. So either winds that strong are rare, or they only happen in storms or something like that. But that seems to be what's driving the activity, is the very fastest winds that are relatively rare.
Oh, right. That is actually really cool, because you can click in on that. You can see right here, this is where he's talking about, guys, that little red area that is to the right of the reflection of the sun. Is that what you said? You said that? Yeah.
Yep, that's it.
So how much does Saturn illuminate this puppy? I mean, I know Saturn's reflecting sunlight, right?
The correct side,
right?
Such that you're in the sub-Saturn hemisphere. You do get a significant amount of light from Saturn, in that Saturn is relatively large in Titan's sky. You're standing on the surface, of course, you don't see it as much because the haze is in the way, so the light gets scattered, but it still filters down. So even if you're on the sub-Saturn hemisphere on Titan, you still get some light even in the middle of the night. On the anti-Saturn hemisphere, though, once it's dark, it's fully dark.
Interesting stuff. I love it. I don't want to take up too much more of your time, though, and I do want to see if anybody does have questions, unless there's something really cool about Titan that you really like talking about. Is there something super cool what knocked your socks off about Titan?
Well, we've talked a lot about the cool stuff on Titan, I think. I'm just real excited. Cassini is obviously ending on Friday. It will be sad to say goodbye to the spacecraft. I mean, I've been working on it my entire professional career, essentially, since I graduated from graduate school. I've been working on it continuously. It's gonna be so weird not to be getting data from it anymore. But the good news is it's it's going to die a hero. It's going to go out in a blaze of glory, and it's out of gas. Literally, it's out of hydrazine that it needs to be able to maintain its attitude. So there's nothing that we could have done to have extended its lifetime. So NASA really did well by us. They supported Cassini all the way through to its full scientific mission. So I try to tell people, don't be sad. Don't be sad that we're losing Cassini. This is the natural way of things. All things end. And Cassini really has had a completely full scientific life and has done great things, and it should be celebrated.
It's the circle of life.
Right.
Yes, new missions have to take its place. And that's the next hard problem, is that, Cassini was first conceived of in 1982. And so in order to get a mission out to the outer solar system, it takes a lot of time. You got to plan ahead.
Mm-hmm.
So we're actively trying to plan the next mission now, but it's hard. The mission a couple of missions I'm working on are a Titan orbiter that was proposed to New Frontiers, and a Titan lander. And the Titan lander concept is particularly cool, I think, because the whole thing is a quadcopter. So after it lands, you got this thick atmosphere and low gravity. After it lands, it can spin up the rotors and take off and fly and land somewhere else. And it can do that, every Titan day, every 2 weeks, for years, because we're nuclear powered. So we got some really good ideas for how to get back to Titan in the Saturn system, but it takes a long time.
Oh, wait, I do have something I want to ask you, because I do talk about this. I just touch on it. So Saturn and Jupiter, everybody thinks, well, they must be pretty similar, but I talk about, Saturn being rather buoyant. If we had a big tub and we dropped Saturn in it, unlike Jupiter, well, that'd be one hell of a tub, guys,
right.
but it would float. Can you elaborate as a planetary scientist a bit more on why that would happen?
Yeah, well, it turns out the radius of giant planets, and this is something I know that Jason Steffen knows, the radius of giant planets isn't kind of intuitive. You start with a small, low-mass planet. You keep adding stuff. You start with, say, a Uranus or Neptune style 15 Earth mass planet. You keep adding hydrogen. It gets bigger and bigger, right? Well, yes and no, actually. Once you add hydrogen up to 4 Jupiter masses, if you keep adding hydrogen, the radius starts to shrink as the extra gravity of all that hydrogen starts to smush everything down tighter and tighter. And so one of the reasons Saturn is so low density is that it's a third of the mass of Jupiter, but it's 0.8 of the radius of Jupiter. So because you have less gas in Saturn, it expands. It doesn't have enough gravity to contract itself as well, so it's lower density. But there's other differences between Jupiter and Saturn as well. For instance, you look at Jupiter, you see all these colors, right? And you look at Saturn, it's white, okay? Yellowish, but white. It's not clear what's causing those colors on Jupiter and why it's not causing those on Saturn. Furthermore, Saturn is really weird. We just don't even know whether it has a core or not. If you look at computer models as to whether it has a core or not, we think Jupiter probably does have a core, but right now, we don't know, and that's part of what Cassini's final mission is trying to find out, get in close and measure the gravity. But it seems like their interiors might be quite different in terms of how many initial heavy elements they had, whether they were nucleated around a core, whether or not they've it's been suggested that Saturn might have the conditions for helium rain, where the helium and hydrogen, when they're down in the interior, don't mix well, and so they kind of separate out like oil and water, and the helium rains down to the core. And that doesn't happen on Jupiter. So they're actually surprisingly different worlds, considering they're both mostly just hydrogen and helium gas balls.
Yeah, no, Jupiter's got that metallic hydrogen. Yeah.
Sorry, say it again.
Jupiter's got that metallic hydrogen going on.
Yes, both Saturn has liquid metallic hydrogen as well. It doesn't have as much, but if you go down far enough the interior of Saturn, it also is able to liquefy its hydrogen. And I think if we went to these exoplanets that Kepler's finding, we'd just find a shocking diversity and variety of different kinds of planets, depending on their mass, their composition, how far they are from their sun, and how evolved they are. And I think we're going to enjoy exploring those over the next couple decades with James Webb Space Telescope and other similar future missions.
Yeah, I know we have the Europa Clipper mission, which Enceladus and Europa have exhibited similar behaviors, yes?
Yes, somewhat.
Somewhat.
Europa is much bigger than Enceladus,
Mm-hmm.
but it's also the surface is entirely water ice, and it looks very active, as if there's some sort of ongoing activity. And there have been suggestion that maybe there have been some on again, off again plumes on Europa. So we are actively planning this mission to Europa, moon of Jupiter, called Europa Clipper, that would fly by Europa. It would actually stay in Jupiter orbit and fly by Europa when it came down in close a couple times, once every couple months. And that's our big next mission to the outer solar system. That would launch in 2022 and arrive in 2030. So it takes a while to get out there.
Yep.
So I guess that's one of the advantages of astrophysics missions, is that you kind of start taking data right away.
Blows my mind, man. You have no crews. We all plan, oh, we're going to launch the thing, and then we'll spend 7-year cruise writing all the computer programs and stuff, because there's obviously no rush, right? You guys launch and you blow off the cover and you start taking data. It's just, wow, it just blows my mind.
Yeah, so people are saying not that far off. Let's see. Does anybody have any questions, or mods? Did you guys gather any questions in here? Let's see. Or Dr. Stefan, did you see any ones?
I did see a few. Some of them I answered as we were going. It has already been an hour. Yes.
Mm-hmm.
Do scientists make bank?
I said no.
We do fine. We're not in the poorhouse.
Not in the poorhouse, but not rolling in it.
I'll tell you my salary. When I started here at University of Idaho, I was making $55,000 a year, which is not very damn much, but it's pretty cheap to live here. Now they're paying me $75,000, I think, a year, and I get if I bring in some grant money for the summer, I can augment that up to about 80 or 90, and it goes real fast. I have 4 kids that I didn't have when I first moved here, so they burned through the money.
So he accumulates maybe about 10 to 25K a year, with including the 4 kids. No, I'm kidding.
Left.
Oh, so quick question. This came up in the chat, and I think I answered it correctly. But why is this image that we're seeing of Titan with the blue, the one that you made with the blue haze, is that like approximately what you would observe if you were there? And
not close. No. If you're looking at it with your eyes, all you'd see was an orange billiard ball. And in fact, that's what Voyager 1 saw when Voyager 1 flew by in 1979. They, instead of going on to Uranus and Neptune, they sent Voyager 1 to Titan because it was more interesting than Uranus and Neptune combined, right? But it turns out the smog is so thick, you couldn't even see through to the surface at all. So that's one of the reasons Cassini was designed with the radar and the infrared camera, so we'd be able to see down to the surface.
So where does this color scheme come from that you have on this one?
Yeah, this is Jason color, the one I invented. Basically, there's a lot of scattering at visible wavelengths, so you can't see through. As you go to longer and longer wavelengths, essentially the haze particles are about a micron in size. So if you start looking with wavelengths, all right, 5 microns, you can see right through the haze. And so in the near infrared, you can see through the haze, but the methane, yeah, that's a Voyager 1 picture right there. The methane absorbs a lot of light in certain wavelengths too. So it turns out there are about 7 or 8 windows, we call them spectral windows, particular wavelengths where you can see down to the surface of Titan through the haze where the atmosphere doesn't absorb. So I picked the 3 of these that show the greatest surface diversity, actually. And those are 5 micron region, which is 10 times longer light than your eyes can see, 2 microns, and 1.3 microns, which happens to show water. If there's because water absorbs at 2 and 5, but doesn't at 1.3. So water ice appears blue in my color schemes. So if you can see there's some blue in the image that Skylias has up now, and that's areas that show enhanced water. But now this is essentially a color scheme that I came up with that kind of shows the most. It's not false color. People call it false color. That is not true. Okay. it's real color. It's just not true color. It's not the color your eyes would see. It's a particular near infrared color that maybe if you lived on Titan, you would have evolved eyes to see at these wavelengths because they're really the best in terms of seeing what's going on. But they're not what you would actually see if you were there.
Okay.
And you
so
studied,
I was wrong.
Yeah, so you studied this a lot in the visible light, though, didn't you?
Visible light, you really can't see much.
Okay.
On the other hand, if you were down under the haze, if you had a lander, this Titan quadcopter we're proposing, all the cameras on it are optical. And the reason for that is at the surface of Titan, all the scattering from the haze makes it always looks like it's an overcast day. It's overcast here today in Moscow. And so that overcast still illuminates everything, but it illuminates things diffusely. So you can't see that light if you're trying to look from orbit because it gets scattered away. But if you're on the surface, actually optical light works fine. So our camera has 3-color optical cameras on the quadcopter, and the Huygens images were taken in the visible as well.
Awesome. I'm going to ask. We got a few questions here. So. If you have time, if you have to go, I understand too, because we've gone over. Okay,
let's do it.
Just making sure. Does the atmosphere on Titan have more or less mass than the atmosphere here on Earth?
Let's see. Well, the surface pressure is 1.5 times. The density is 4 times. But so the pressure is equal to the pressure at the surface of a planet. Actually, where does that pressure come from? It's equal to the mass of atmosphere all the way above you pushing down on you. So the total mass per square meter on Titan must be quite a bit higher than on Earth, actually. But the radius of Earth of Titan as a whole is smaller. Right. So the total mass, I'd have to calculate exactly where it's at. It's probably comparable. There's more in a given column of air on Titan than there is on Earth. But with the lower total surface area, the total mass of the atmosphere is probably about the same.
And what's the surface gravity compared to Earth?
Yeah, good question. It's about the same as our moon, actually. So it's about 1/7 of the gravity on Earth. So it makes flying this quadcopter a breeze. It really is the right solution. We were trying to think of how you do what the Mars rovers have done on Mars with wheels and stuff. But you go to Titan, everything's cold. You're going to be touching the surface, and it could be gunky. And you don't know whether the surface is trafficable, whether there's so many crags and rocks you wouldn't be able to drive on it. And really, it makes more sense to just use the atmosphere, fly up with your quadcopter and fly where you need to go, and not drive over the places between.
So Hammerfall asked, do you guys have good storm data or data? Obviously, that's plural, even though it is tidally locked.
So, yeah, I mean, the fact that it's tidally locked doesn't really affect the storms too much, except that it means that they're in different places. The atmospheric circulation on Titan, for instance, doesn't have the same Hadley cells that we have on Earth, so that doesn't have the same sort of overall structure, and it moves back and forth. It seems like the summer hemisphere typically has the upwelling air that causes thunderstorms and rainfall, similar to that you get at the tropics on Titan. Just kind of seems to follow the sun and moves north and south with the sun as it goes. But it's so that in that sense, it's affected by the slow rotation in that it's able to do that, which it wouldn't be if it were rotating faster and had a stronger Coriolis effect.
Okay, and someone said you mentioned the size of the granules on Titan is quite a bit larger than average Earth sand granules. Do you know or have an idea of what causes those differences? Are the granules pretty uniform in size from what you've been able to see?
Okay, well, the grains on Titan, we actually don't have any observational constraints. If you calculate from first principles how big an organic grain needs to be in order to be able to be saltated or moved in Titan's winds, it turns out to come out to about 200 to 300 microns, which it turns out is almost the same exact size as sand grains on Earth. So the grains we think should be about the same size, but we don't know. The Titan quadcopter I want to send to Titan, we're going to land on the dunes and scoop them up and look at them in high resolution, and we'll know exactly how big the grains are. Furthermore, we should be able to measure how rounded the grains are, right? Old sand grains on Earth tend to be nearly spherical, whereas new grains tend to be really angular and craggy. And that'll tell us something about how old this whole sand sea system is and where the sand comes from and where it goes to on Titan, which is one of the outstanding questions we have after Cassini.
Mm-hmm. And then that leads in beautifully to Joe's question. What's the plan for Saturn and Titan after Cassini? I mean, you kind of touched on it a little bit, but
there's no plan. There are proposed missions. NASA has different kinds of missions. One are the very large spacecraft that, like Cassini is, and like the Europa Clipper will be, that are designed by NASA, and individual scientists put experiments on them. The other kind are competed missions. And so the New Frontiers competition that's going on right now actually is one of those, where you have up to $1 billion to design a mission to a particular set of destinations, and Titan was on that list. And so we proposed this Titan orbiter and Titan quadcopter to New Frontiers, but we're competing against 12 total missions, some of which are also going to the Saturn system. I know at least one Saturn entry probe that would fly into Saturn itself with a parachute and take observations and measurements on the way down through the atmosphere. And there's at least a couple of Enceladus missions as well, flying through the plume of Enceladus and trying to really characterize the organic material that's coming out of those plumes that may be coming directly from a subsurface ocean that could potentially be able to harbor life. So that's a really important measurement to be able to make in terms of what those.
Do you think that they would impose a shotgun wedding on any of these things?
I hope not. It turns out, and this is something Kepler really helped teach me. I think it was before you joined Kepler, but when I was there before we launched. I visited Lockheed Martin, and they say no spacecraft can launch until the weight of its paperwork exceeds the weight of the spacecraft. And so they were just like reams and bookshelves full of manuals and material that they saved, just a ridiculous amount of just paperwork. And so shotgun marriage, you think, oh, that makes it cheaper because now we only use one rocket. But now you have to redesign everything, a whole other layer of bureaucracy above those two parts that then have to be able to talk to each other. It turns out that's even more expensive than doing two separate missions. So I'd rather just send two separate missions and have them not affect each other.
This might be a little bit of a split up question, but could you ask how the sensors work? Someone said actually where they get back to the bunch of numbers. I'm very curious how they turn numbers into a picture.
Okay. So the way we turn numbers into pictures is not too dissimilar from the way your iPhone does, right? We have a detector made up of, if it was your phone is made up of megapixels, right? 14 million little detectors, each of which is sitting there. And when a photon hits it, it knocks an electron up into the conduction band, and we're able to count those electrons and measure, therefore, how much light had fallen on that pixel. Remember, I said Cassini was designed in 1989 and launched in 1997. And we're an infrared instrument, which is harder to build than an optical camera. The optical camera has 1 million pixels, 1 megapixel. We actually just have 1 pixel and 256 different spectra. So we disperse the light with a prism into 256 different colors. And actually, we only take data from 1 pixel at a time, believe it or not. All these images, these sort of greenish images that I made, 1 pixel. And what we have is we have a little mirror that keeps moving around. So we stay on 1 pixel for 1 second and then go to the next one, then go to the next one. And we build up tiny little 64 by 64 pixel postage stamps. And that's why it's worked to be able to, sort of sew those and knit those into these single pictures. And any future instrument that was sent to Titan will be much better. The Titan orbiter that we're proposing, for instance, has a 4 megapixel near infrared camera that will just be amazing. Totally nail Titan and be able to see. We'll get global imaging at 25 meters per pixel. It'll be able to really just totally revolutionize our vision of what's happening on the surface there.
Yeah, New Horizons did pretty good with their imaging as well, guys. I don't know if you guys have saw the pictures that we had previously taken by Hubble of Pluto, and then when we had that closest approach, and the stuff that came back on Pluto was unbelievable.
It really makes a difference if you go there.
Yeah, it does. It does. So we definitely, it'd be great to go back to this guy because they're so important to understanding solar systems as a whole. And again, we don't observe these kind of moons really in other parts of our solar system orbiting other planets. We don't see these atmosphere-rich moons. I mean, this is very cool.
Right?
Yeah, I don't think there's been really a planetary mission that's gone out where they haven't been surprised by the majority of the data that they took.
Well, it's not necessarily the majority. I mean, you do design your mission so that it'll be able to answer some questions. But a well-designed mission will then also be able to see things that you hadn't even thought of, right? And come up with new questions that will hopefully drive the next generation. And Kepler's been the same way, right? I mean, we've discovered, like, how is Kepler 11 possible with 5 different planets all super close into their star, all in these really circular orbits? Totally crazy. No one anticipated things like that. And so a well-designed mission can both answer known questions and show us the next questions to ask.
I think that. Oh, does Titan have earthquakes? That'd be more.
Great question. We
that
don't
is.
know. But our Titan quadcopter has a seismometer, so we hope to find out. And using that seismometer, we'd be able to determine what the interior structure is, how thick the water ice crust is, and what the nature of the liquid water ocean is beneath it, and how often and how much tectonism there is moving the crust around. It's one of the things we hope to be able to get to.
Very cool. Well, I know that he was very generous with his time, and same with Dr. Stefan. But again, guys, is there stuff still coming back from Cassini with Titan?
We just got new data today from the last flyby, and it's really cool. It shows a specular reflection like this one we saw in the T104 image, but it's really far south, and honestly, we're still processing it. So I don't even know what the rest of it has, but it's kind of bittersweet. And these looks like really cool new data, but this is the last. This is it. That flyby, Titan flyby, is the one that's directing Cassini into Saturn's atmosphere, where it'll burn up Friday morning.
Yep, and we're going to be streaming that, guys. But yeah, I mean, I'd love to have you back if you guys find anything else out. But are you going to be doing more work with some of the exoplanet stuff that's going to be coming to fruition, especially with the James Webb Space Telescope? I bet you guys are going to have a heyday.
Well, I'm actually more looking forward to the more. I guess TESS is launching about the same time, huh, Jason? So this is a sort of a Kepler-like instrument looking for transiting planets, but looking for them all over the entire sky. And so I'm really excited about the prospects for that. No offense, James Webb was designed to find primeval galaxies. It's not really an exoplanet mission. It'll do some exoplanet stuff, but I think it's going to have to wait till the next big astrophysics mission before we'll be able to do the really good exoplanet stuff that I think we should be doing.
Well, then maybe we need to have an exoplanet discussion with 2 of the Kepler guys here. So that would be interesting.
That'd be fun.
Do that.
I think that sounds really good. And thank you so much, Dr. Barnes and Dr. Stefan, as always, for your time. I appreciate it.
Thanks for
your
having
time.
All right, guys.
Cool. All right.
I'm gonna let you guys
Enjoy
go.
The crash, guys.
Yeah.
All right.
We'll see you. Good luck.
See you later, guys.
All right. Bye.
Bye-bye.
Bye.
I love him. He's amazing.